every time we start a module, we're doing firmware system this time. What you are going to need to do is log in to your GitHub desktop. You don't have to be online as long as you've done what you're supposed to do in the GitHub module, where you've created a GitHub account and you forked the Nginx Razor branch and you've pulled that down to your local machine and you tried building it. That's what everyone was working on the other day. Okay. So as long as you've done that, once you have your local copy, unless I say, oh, I made an update that you really, really need to get, then you can just work locally. You don't have to worry about what's happening in my branch. I do suggest that you sync your changes. So remember, when you're working on your local machine, even if as you're doing commits, that's only on your local device, okay? Which means if someone steals your computer, all your code is still gone. If you click this sync button in GitHub desktop, that actually pushes it up to the cloud, or there's a command line version to do that. Okay? So then it's actually in the cloud, and you can look on github.com and you'll see your little message there that said, you know, this commit was taking place at this time, and you know it's in there, right? So now it's safely in the cloud and on your local machine. Okay, so I suggest you do that all the time, right? Again, really try and do this in your labs. Doesn't matter if it's your 511 lab, doesn't matter if it's whatever your C program course is called. Use GitHub and get to know that, whether you use the desktop version or the command line version, doesn't really matter. So every time we're going to start a new module, we're going to start with a clean build of code. So if you've been working, so I've been working on this branch, sorry I don't have a pointer, I've been working on this branch called EiE book. I'm writing a textbook, I'm doing some updates for this code, so that's the main branch that I'm working on. As long as I have committed and everything is saved, in this section here, it'll say no changes, right? So GitHub is always keeping track. As soon as I change one thing in that project, even if I open the project, then there's going to be a change in recognized by GitHub, and you'll see this. If you have a change pending, you're not allowed to switch branches, okay? Because as soon as you switch branches, it's going to take out all those files that you've been working on, and it's going to put in different copies for the different branch that you're going to, okay? So everything is overwritten, okay? So if you haven't committed it, and there is, I don't know if you've seen this, in the main repository directory, there's a .get file, which is, I think it's usually hidden, but it grows and grows and grows. And that has every single copy of your code that you've done, all the branches, every change you've made. So over time, this thing is massive. Okay, so we don't tend to keep, we like to clean out our repositories now and then. So you have to keep an eye on that. But all those changes are there. That's what allows you to change branches. That's what allows you to revert to previous changes and things like that. Okay? So once this is set up, you can either discard the changes or accept your changes. You can pop up to where the branch selection is. And we always want to start with a master branch. Okay? So you're going to click on that, and that's going to automatically change over your files. And then, because we're working on something new, you don't want to work in your master, right? That's not your working copy, right? If you rec master, you don't have the main branch of code, right? So our branching model that we briefly talked about, we'll always have our master stream, and we're branching off to work on each module as we go through. Okay? So if this is probably a slightly older GitHub desktop, but it's whatever you're using, you'll see kind of the same thing. So we can create a branch with this here. So we do that, and I'm going to just call this by the date because that's the easiest thing for me to do because I get a lot of these. And this is Firmware System. Okay? So you can see, make sure that it's from branch master. Okay. If you're in a different branch and you're branching, you might branch from the wrong thing. So you always want to be really aware of what you're doing, right? Don't ever make assumptions. Assumptions are the worst thing you can do, or one of the worst things you can do in engineering. Okay. So make sure you check everything explicitly, or else you're going to go down a path that becomes very confusing for us to figure out where and why you're at a particular place. So, create new branch. So now, I mean, nothing looks like it really happens, although you see this little doohickey here that says, I mean, it's kind of a graphic depiction of your master branch and your new branch there. I don't really ever look at those things, but whatever. Remember, this is local, so if it's local and hasn't ever been pushed up to your Git account, then the word sync actually says the word publish. Okay? So if you want, you could publish this, and it'll whirl and twirl for a bit, and then you'd see that branch in your GitHub desktop. You don't have to worry about it right now. What I would then suggest, since this is your first time running this code, is right-click over on your repository name. In the new GitHub desktop, it's over along the top there that has a repository link. And you want to find the thing that says Open in Explorer. Okay? So this will just pull up an Explorer window for you. And it takes you right to where your repository lives. Okay? And that's good because if your repository, if you can't remember where it is, or you've got several of them, this takes you right there. Okay? And what you want to look for is firmware ASCII. Okay? So this is all the specific files for our ASCII development board. And we haven't really talked about that much, but this screen is just a very simple, very classic LCD screen that we just send ASCII characters to, and out they come. I've also got a dot matrix board where you actually have to send literally the dots of what you want to put on there. So this code supports both. We're working with the ASCII version. And if you downloaded the EiE version that I recommended, okay, you want to choose EiE 720. If you're using a newer version, EiE 8, you can use those project files there. I don't like EiE 8, which is why I'm not using it yet. And because I have both installed, I'm going to fire up EiE here. So you can see I've got a folder with all of my EiE tools in it. Okay, I suggested you do that. It's actually all my engineering tools. Okay, right? I've got everything that I use all the time, okay, right there. Right? So in EiE, we're going to be using this. We're going to be using TerraTerm and maybe some other stuff as we move along. So EiE pops up, and to make sure my version, you should be able to just double click the EWW file, but because I have two EiEs, I'm going to click and drag this, okay, and in we come after we spin for a little bit. What we're going to do today is we look at Firmware System. Who's heard of the term bare metal? The answer is everybody, because I just told you what it is, or I'm about to tell you. So when we're talking about embedded systems, you're going to come across two sort of scenarios. One we call bare metal, and one we'd call with an operating system. Okay? So an operating system in the embedded world, you probably haven't come across one yet. It's not like an operating system like Windows, right? Windows is pretty big, it doesn't fit on this kind of processor. You can put things like Linux on this processor, a very shrunken down version of Linux, right? So that's an operating system. But there's a lot of embedded OSs designed. I do a course in a program or an operating system called FreeRTOS. RTOS, which is usually what we do for embedded, is real-time operating system. Those are the useful operating systems. Non-real-time operating systems tend to not be that useful for embedded because you need to have immediate response. You need to have guaranteed execution time. So there's a lot we can say about operating systems. And if you like embedded, if you're going to get into that stream, I'd highly recommend at least getting a book or taking a course in operating systems. I think the software stream does that. I don't think Computer Eng does yet. Anyways, I'm not going to talk too much about this, but what you do know about operating systems, like something about Windows and how you're coding in Windows already in your C classes, is that you don't have to worry about anything, right? You've got the libraries, you've got the operating system protecting you. You just write your code. If it breaks, who cares? You kill the task and whatever, right? It's doing all these things for you. But that takes a lot of processing power, right? Your application's running. I think all operating systems are multitasking. So yeah, your task is going, but then, if you're using Windows, you got your browser going, you got all these different things going. In an embedded system, you might have a task that's running your LCD, you might have a task that's running your buzzer, you might have a task that's running your serial output, your LEDs, all these different things actually need processor time. Remember, we can only do one thing. And in any computer, it doesn't matter if it's a small 8-bit embedded system or a 64-bit machine that you're using right now, a processor core can only do one thing at a time. Okay? So yes, we have multi-core processors now, so yes, you may be doing a few things in parallel, but if you think of one processor and one core, each one can only do one thing at a time. And before we had these multi-core systems, Windows ran, it still looked like everything is going, you're listening to music, you're writing Word documents, you're playing games, right? It looks like everything's happening at the same time. It's not, right? It all boils down, but the operating system is managing that for you. It's taking your task, giving you a little bit of time to run, taking another task, giving it a bit of time to run, taking another task, doing that, and it keeps going through on a schedule, okay, which is called a scheduler, and that's a big part of an operating system. Okay? So we can only do one thing at a time. Okay? If we have multiple things that we need to do, we have to schedule the processor time to do them. Okay? And that's kind of the fundamental thing that an operating system does, right? It does other things, yes, but the biggest thing that it does is allow you to forget about everything else that's happening in your system and just run your code and assume that your code is going to run as if it's the only thing in the system. Okay? It's not, but we're going to run it like it is. Okay? So that makes things easy, but you're looking at a lot of extra code to start and be running on your system, potentially with bugs, potentially with power consumption, all of that, before you can even start running your system or running your tasks. So that's all I'm going to say about operating systems. A bare metal system has no operating system. Okay? In most cases, I think every product that or almost every product that I've designed, at least in the first 10 years of being an embedded designer, we always wrote our own code from scratch, always bare metal, okay? Which means that we'd start with a blank processor because we'd be doing very, very specific applications of products and things like that, and write that from scratch, write some low-level drivers to make the different parts of our boards work, write some sort of system that goes through and makes this product work, okay? But no operating system involved whatsoever. The way that most of these work in an embedded system is just a big loop, okay? And they sometimes call it a super loop because it's just a linear progression through a bunch of function calls, right? Update LCD, read sensor, sound alarm, blink light, sleep. Update LCD, read sensor, sound alarm, blink LED, sleep. Over and over and over again for its entire life. That's all it does. Task, 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 function call, function call. Okay. Sleep is really important in embedded systems, especially if you're running on batteries, okay? Because when you're sleeping, the processor's not doing anything, right? Just like this person is almost asleep. I caught you. No, not you, this one here. So we go to sleep when we don't have anything to do. And embedded systems, even though this processor, it's clocked at 16 or 12 megahertz, but we run it at 48 megahertz with some hardware on the board. So 48 megahertz is super slow compared to your phone or your computer, but 99.99 times or percent of the time that this thing's running, it's asleep, okay? Because it can do things still so quickly that it doesn't have to worry about that. Okay? So in a bare metal system, we have a choice of designing how our system is going to run, how often it's going to sleep, and what it needs to do. Okay? In most systems that I've worked with, if you wake up every, say, 1 millisecond or 5 milliseconds, that's plenty of time to do whatever you need to do and then go back to sleep. In some cases, you can wake up every half second. So I used to build gas detectors, and we could just sleep for 500 milliseconds, wake up, read a sensor, see if anything's going on, no, go back to sleep for another half second. So from a user's perspective, right, they'd be looking at a display, and the display would be updating twice per second, which is tons, right? The concentration of oxygen in this room doesn't change very often, right? If I breathe on a gas detector, I actually will reduce the oxygen level, okay? So then I'll see that the screen level of the reading go down. And twice a second is plenty, right? It's not something that needs to react immediately. Okay? However, if you were doing something that maybe was a sensor, so you have a board there and a board here, and you're trying to do a system for catching time, if you ran past the sensor, right, if I was only waking up every half second, I'm going to totally miss me running by. Okay? So in that case, if you were maybe updating every millisecond, that's probably enough. It probably took me maybe, what, 100 milliseconds to cross that distance, right? So if I break that down into 100 millisecond steps, right, that's plenty of resolution to capture, you know, to get a good result. Okay? If this is Olympic time trials, then maybe I want to do 1,000 times per second, right? Because you can get that close. So depending on your application, you're going to code your system differently. Okay, so that's something to consider. In the EiE system, and this is what we're talking about today. So when I was designing the firmware system for EiE, it is based on a bare metal system, but it's a little more fancy, and it starts to approach what an operating system does, because I wanted to have a really, as best I could, a nice multitasking system. This just tells you how to get things started. So I'm going to call this a pseudo operating system. So of course you have this all, and today in any module I'm going to introduce the main ideas, but you still are going to follow through the web page at your own pace to go through and do what you need to do, and then you're going to do an assignment. Okay, so I emailed all the assignments today, and as we go through, there's also these little skill checks that I've put in there. So those are kind of like self-tests to make sure you're kind of following along, picking up the main points that I expect you to pick up. Okay. This is how the EiE firmware system runs. Okay, so it still looks like a big loop, but it's got a couple of rules. Okay, and the rules kind of replace all the fancy code that a normal operating system would have to have. Okay. So there's two sections of this. Okay. There's an initialization section, and there's a main loop section. Okay. And there's different rules for these two sections. Okay. So in initialization, okay, you can see there's three sections here. So what we call low-level initialization, drivers, and applications. Okay. And you'll get to know more what that means as we go through and start and learn more about embedded systems. But there's sort of three things you need to get going, okay, to make sure your processor's going. So under low-level stuff, that's things as fundamental like, where is my clock? How fast is my clock? What is hooked up to my processor? Okay, so like very directly hardware-related things. Okay, and you can look at this code, and we don't talk about it too much in EiE Firmware 1, but we talk about it more in different classes. Then you get into drivers. So these are little bits of code or tasks that are running or going to be running that are going to manage things like the LCD, right? So you can, write a string to the LCD through an API function, and the driver is going to make sure that it takes that string, parses out character by character, talks to a peripheral, communications peripheral on the processor that talks to the LCD, make sure those bytes are going back and forth properly, and make sure your messages is going out all right. Okay? So those have to be initialized, and then you have applications running on top. Okay? And this is mostly what we're going to write to make things make the board do things as we're going through these different exercises. Okay? So the main rule in this section of code, okay, your initialize function or any of these initialization functions, they're allowed to take as long as they want. Okay, so when Windows is booting, right, and it just spins or whatever, right? You have no idea what's happening. Okay, that's like what's happening here. Okay, so you can't run any programs, right? There's no responsiveness from the system. You just have to wait. Okay, so fair enough. Okay? The only rule then is that whatever you're doing, so if you want this long, complicated boot up sequence that you're blinking lights all over the place, and there is a short light blinking sequence, you're allowed to take as long as you want, okay? But you have to make sure that no matter what, so as long as it works, that's good. Even if it doesn't work, you got to exit out somehow, right? So your code should be robust enough that if you're booting up a task, it can't fail. It can't stop and hang the system. It is super easy to hang a bare metal system, right? Easiest way anywhere in your code. If you want to stop your code, do this, okay? And your board will freeze as soon as it gets to that line, okay? And why would you do this? Well, it's actually really helpful for debugging, because you might want to stop your code in some spot. Things are going to happen so quickly that you might need to I want to stop, a bunch of stuff is happening, I need to stop the code. Okay? So you can do something like this, right? In an operating system, if you hit a while one loop in your task, okay, as soon as the scheduler, say if you're given 5 milliseconds to run your task, you can sit in this while loop for 5 milliseconds, and then the scheduler will say, well, someone else is going, so it runs everything else, comes back to your task, lets you sit in your while loop for another 5 milliseconds, who cares? It'll keep doing that, the board will seem to work. In this code, in any bare metal system, unless you have some way to detect this, which you don't think you can, unless you have an operating system, your board is just going to freeze. Okay? So don't put a while one loop in your initialization. Okay? Don't put anything like waiting for a user input, right? That's really dangerous. What if there's no user? Okay? Or waiting for a response from a sensor, or waiting for something, right? If you're waiting for something in an embedded system, what should you do? What's a great practice if you're waiting for something to happen that may or may not happen? Sleep is a good thing. Yeah, that's one thing. What else? Progress bar, yes. In a small system, we don't have maybe that kind of capability.
So like a maximum of time that it needs before, like that it needs to respond before it needs to run.
Yes, a timeout. Okay, code timeouts everywhere that you can stall or get stuck, right? Have something that's going to run out. So if you're conditioned on a user input or a sensor reading or whatever, also condition on a certain amount of time. Okay, that's a huge thing that you can do. Okay, and it doesn't have to. I mean, in initialization, it would be good to print out on the debug or on the LCD if you can. You know, a timeout occurred, the application didn't start. But I'm embedded. We can kind of get away with some stuff depending on the application. If it's just if it's a dumb system that's hidden somewhere, you don't need to have that kind of stuff. You don't have a progress bar. You can't show that. All depends on what you're trying to do. But regardless, you don't want to get stuck, right? So have a timeout. Okay. So that's sort of the one and only rule in this initialization section of the code, right? Don't get stuck. Get out somehow, even if it's broken. Okay. And you'll see when you boot your board, if you're looking in Terraterm where the serial output's coming, you'll see all the tasks reporting that they have started. Okay? Or not started, or failed, right? So you'll see through that, and in the end it'll say initialization complete. It'll give you a list of failed tasks, and then it'll be ready to run. Okay? So the next part is kind of the more important part, and we call this a super loop. I don't know why, that's not my word. It's a super loop because it does many things. It's kind of like a sequence of function calls, but it's a little bit more. Okay? In this system, we run a sequence of state machines. Okay, so you've covered state machines a little bit in 353, I think, maybe. Not yet? Okay. I'll draw you a very quick picture of a state machine then. So think of a system that has, think of a car. A car is probably a good system. So when you start your car, let's go here. Okay, you go into your garage and you see your car. Okay, I'm assuming everyone knows what a car is and generally how it works. In China, I can't do this example because they don't know. So your car is off, right? So in order to get going, you need to start the car, right? So we need to put the key in the ignition and turn it on. Okay? If the car is off and the key is not in and you turn the signal light on, nothing happens. If you step on the gas, nothing happens. If you turn on the radio, nothing happens. The key's not in, right? So this is a state. It's the off state. Okay? And the only way to move to something else is this condition here. So key in the ignition and we start, car starts, now we're in idle. Okay? So now our gas pedal works, right? So we can turn on our gas, or we can rev the engine, we can listen to the radio, turn on the lights, do whatever we want, right? So all those inputs are starting to work. Okay? But while we're in that state, so if we, let's say press gas. Okay. So in this state, if we press the gas, okay, we're not leaving this state. We're in an idle state. We're not driving yet. Okay? The only way to get to a driving state okay, is to change gears. So change gear. Okay? So if it's an automatic transmission, you shift from park to drive or reverse. Okay? If it's a manual transmission, you select the gear that you want to start with. Okay? So press gas can happen here, but it doesn't result in a change of state. Okay? The only thing that results in a change of state is changing the gear. Okay? Once we're in the driving state, again, we can press gas. We can switch gears, we can do all these different things. Okay? But the only way that we can get back to this state is if we choose park. Put our car back in park. Okay? So while we're in driving, we do all these things. Okay? The car responds in a certain way, okay? And it does its function of driving. Okay? In this state, our idle state, yeah, it responds to certain things, okay? But it won't leave the idle state until this specific function. The only way we get back to idle state is by putting it in park. Okay? So as you'll learn, a state machine is, like, this is a state machine, this is a state diagram, and it's discrete, like, operating modes, I guess you can say, okay, where you have certain functionality available, okay, some functionality is not available, and if you want to go to a different state, you need to do a specific thing. Okay, so you're going to learn a whole bunch of things, like in our system, for example, a button press might take you to a different state, or an input from a sensor might take you to a different state. Okay? Each of these sections, drivers, applications, and system sleep, so I guess it really kind of breaks down to drivers and applications. These you're going to see is a list of different tasks. Okay? And the tasks, I kind of use the terms task, application, state machine. There's one more, I can't think of it. It's all kind of the same thing. Okay? It's like your little, a particular program running. Okay, and I'll try to use task most often. Okay. So we have a bunch of driver tasks. So again, we have LCDs, buttons, LEDs, the serial drivers, the buzzers, all these different things. Okay. Those are the driver functions that need some processor time to make things happen. Okay. And you don't know what exactly is happening, right? They're in different states of their state machines. Okay. But the functions in here just say run the active state. Okay. So whatever you're doing, you're going to get a bit of processing time for whatever state you're currently in. Okay. For you guys right now, you don't need to care about anything else that's happening. Okay. We're only going to work in something called a user app. Okay. So you're going to have one .c and .h file that you're going to write all your code in for your modules. And you're going to assume that everything else works correctly. So these functions are going to run. And then, in the remaining time, the system goes to sleep. Okay. This is a big while loop. Okay. So there is a while one loop in probably every embedded system. Okay. The main code that runs sits in this perpetual loop and runs forever. No embedded system gets to the end and stops and shuts down. Okay. It always keeps and keeps running. Okay. I chose this amount of time, so by the time this first driver is called, everything else goes through, goes to sleep, and wakes up. This is always 1 millisecond. So we're going to call this our system tick time. Okay? So like a tick of a clock or a heartbeat. I know people use both of these things, both of these terms. So our system tick, or our heartbeat, is how long? 1 millisecond. Okay? So that's not that much time, right? If you think in 1 second that there are 1,000 milliseconds, right, that's pretty quick. Okay? There are about 10 tasks that run in this system already. Okay? And what I said to you is that this system is still sleeping most of the time. There's a little red light right by your processor. That is our system tick output. If you stick a scope on there, and this is something you should do, we don't have scope probes, do we? No, we don't. If you have a chance to have an oscilloscope probe, well, I'll try and get some. If you stick that probe on that LED. It's an active low LED, which means when, we'll just do it this way. When the signal is high, the LED is off. So in this system, I'll just draw it this way. If you stick a scope probe on, you're going to see a square wave that looks like this. Okay? So this is the time that the processor is on. It's your on time versus your off time. Okay? So this is when it's sleeping in this section. This is when it's running. Okay? So in a normal, just an idle state like this on time is very, very short compared to the sleep time. Okay. What's this period? One millisecond. Okay. So in this time, all these tasks are running. So LED, button, LCD, serial driver, whatever, 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 and then it goes to sleep. Okay. There's a very, very low power timer that runs as well, okay? And it's a very good timer, so the timing is very precise. This is like exactly 1 millisecond. And that's like the alarm clock that boots the processor out of sleep. It says, hey, it's time to wake up, do your thing, run your 10 tasks, go back to sleep. Okay? So when this is happening, right here, we turn off the LED, and then it goes to sleep, and as soon as it wakes up, we turn it back on, okay? And that's what generates that output. Okay? So you can actually get a very rough idea of how busy your system is because of how bright this LED is on. Because you can't see this, it's happening so fast that as this, what we call duty cycle, so this high time to the total time, which is duty cycle, as this increases, the LED looks like it gets bright. Okay? This is a super, super simple analog to digital conversion, or sorry, digital to analog conversion. Right? We can control the intensity of an LED by pulsing it. Okay? The longer the pulse, okay, as the duty cycle goes, the brighter it goes. Okay? So that is your first indication of how this system is running. Okay? If you had to do some serious debugging, you could put a scope probe on that output and make sure that this is proper. Okay? There's also a way in the code to give yourself a little message that says you just exceeded the 1 millisecond time. Okay? So there's lots of tools that are built in. The reason I say this all is because it's critically important and it defines the #1 rule about this part of the code. Okay? And that is that your task that you're going to run inside there can never take longer than a millisecond. Okay? Take that with a grain of salt because your task the total time must be less than a millisecond. Okay? So if you are really, really close to a millisecond, okay, and you have other tasks going, you're going to stretch out that system time. Okay? So you have to be a little bit more aware. Okay? The system is not going to break. It's not going to catch on fire. It's not going to stop working. It's not going to crash your code. But if you're really, like if you put a while one loop, okay, you're never going to sleep. You're never going to run your other tasks, okay, and your board will look like it's frozen. Okay? Or if you wait for a button press. Okay. Then, like inside your code, if you say if or while button is not pressed, wait, okay, your whole board will freeze. So the challenge of writing code in this EiE system is to break down problems into small pieces. Okay. And if you have to wait a long time, like a user input, 10 seconds is a reasonable amount of time, right? So you have to actually write your state machines and design your code to be in wait states. So you'll get a little bit of processor time. You'll go check the status of the button. Oh, it's not done yet? Okay, we'll sort of exit out of my state, let the rest of the system run through, come back, check the button. Okay. We won't see examples of that till a little later on, but what I do want to do, and that's the purpose of this firmware system module, is to have the confidence to know that your task is going to run once every millisecond. Okay? Which means if you want to blink a light, okay, at 1 hertz, 1 times per second, which means you're toggling the state of the LED twice per second, right? On, off, to make it blink once per second. So every 500 milliseconds. Okay. Using this system, okay, without anything else, to make that LED blink, you can, all you have to do is count up to 500. Right? Because every millisecond your task runs, which means if your task, all it does is increment a counter and check if it's 500. Okay? The first 499 times your task is called, nothing needs to happen. But on the 500th time, then you say, oh, I reached 500, I need to reset my counter, don't forget to reset your counters, and toggle the LED. Okay? So inherently, you have timing built into this system. Okay? It's super easy to break. When we get to more complicated programs, you might think, well, how am I ever going to write, the functions that I need to do in under a millisecond? Okay? But this is actually 48,000 instruction cycles of the processor, 1 millisecond. So most tasks, maybe you're going to take maybe 500 instruction cycles. To check a counter, increment a counter and check it, takes about 10 instruction cycles, maybe 20 instruction cycles. Okay? So you can do so much with this system, even in such a tiny amount of time. The only hard part is getting used to what's happening here. Just double checking what's in here, just so I can make sure I highlight it. So this is the rule. So cumulative execution time of all tasks in a single iteration shall not exceed a tick period, which is, how fast? Good. And then it gives you some detail about what it is. Okay. There is a global variable in the system. Okay. So you'll see that all of my global variables, if they are truly global, they'll start with G underscore. Okay, that's one of the conventions that I'm going to use. So you can, when the system starts up and initializes, this starts at 0, okay, and it keeps counting, right? How big is a 32-bit number? It is 4 bytes, so in decimal, how high can you count? 4 billion, okay? So how long in normal time is 4 billion milliseconds? Someone do it quick. I think it's 41 days, if I remember correctly. Okay? So this system, when you turn it on, it can track 48 or 41 days before this timer overflows. Right? So if you need a time reference, right? So if you want to start an alarm a minute after some event, okay, you just look at this timer. Look at when that period starts and wait for it to reach that value. Okay. There is also a system time 1 second. Okay. So that's good for, I think, 110 years. Okay. So with those 2 timers, this board, you can get an entire picture of definitely as long as you'd need to ever run this code. Okay. Unless you're sending this to space. Okay, so if it's going to be on a 10-year mission to Mars, okay, then you need a bigger timer. Okay, don't forget stuff like that. Okay, because that's actually a serious, a year isn't that long. Okay, when you're doing devices. Okay, so you have to accommodate that. Okay. So you've got those 2 timers. We'll mostly use the 1 millisecond timer. There is. These are all of the different functions that are going to run in the system. Okay. And I'll let you read through this. There's a little bit of stuff about the hardware. Okay. So, sorry, it's small. You can look at this online. But sorry, this is also out of focus, isn't it? Let's make it a little bit better. There's a line right here that says heartbeat. Okay, so you're going to see, we're going to figure out how to change this line from a high state to a low state. Okay, that's described in the notes there as you get through it. Okay. But that's all we're going to do in this exercise is either write a logic 0, which will put this low, which means this LED turns on, or we're going to write a logic high, that means that light will stay off. And this code that we're going to write you'll see 2 user applications. I think actually there's 3 of them in there now. So just pick one, user app 1, 2, or 3. And this is where you're going to write all of your code. Yep, that's about it. There's some, because we don't know how to write code to toggle LEDs yet. Okay. There are 2 macro functions. So macros are just kind of symbols that represent some code. Okay. So you don't need to know what's behind that. You can take a look if you want, and you'll see how it starts. Well, you might see how it relates to the hardware, and I'd be happy to show you that. But if you want to turn the LED, that heartbeat LED, off, you just write heartbeat underscore off, just like a function call in your code. Okay. And you should see that in the main loop already. Okay. And that'll turn the LED off. Okay. You can look at what's going on there, but the main purpose of this exercise is to practice this system time and get it to work.